Hello and welcome to another video. In this one, we're going to be covering day 23 of Advent of Code, which was another kind of tricky one. So I actually wrote a lot of code for this one, so I'm not going to be live coding this one, but I'm going to walk you through my solutions to both parts, including a failed solution, and I'll show you why that didn't work and what I eventually came up with. So let's jump into it. Okay, so the problem today, we have an input which is a series of numbered cups, and they look kind of like this. This is actually the sample input. And we're playing a game with a crab. And the crab is going to rotate the cups in a very particular way. I've laid out the rules here. So the cups are arranged in a circle. Here's an example of the same input arranged in a circle. And there is a current cup, which is the first in the inputs, and the first cup is going to be 3. I've marked that with blue here. I'm actually going to run one round of this and show you what it looks like. Then you're going to take the next 3 cups from your circle. So we're going to remove these 3 here. The next, oops, I don't want that. I want the brush. We're going to remove these 3 here. Next, we want to find the target cup. Actually, let's, before I draw all over this, oops. Before I draw all over this, let's copy this over here. And we'll actually draw out all of the different numbers here. Okay, so back to this. We're gonna remove these 3. So we know those are gone. And then what? We find the target cup. The target cup will be the current cup minus 1, or if this is 0, wrap around to the largest cup, or if this is in your taken cups, keep subtracting 1 until you get to a number. For this first one, it's really easy. 3 minus 2 is 2, and that's not in our taken cups. But you can imagine if this were 2 and 1 was in here, you would wrap around to get 9, and then 9 is in here, and you would wrap around to get 8, and 8 is in here, and then you would wrap around eventually to get 7. But in this case, our target cup is this 2 here. And note that we've already, oops, I keep getting the wrong thing here. We have already deleted, 8, 9, and 1 here. Which in a way makes this 2 move up over here. Once we have found our target cup, then we insert the 3 cups that we took out after that. So after this 2, we're going to insert these 3 cups. So we get 8, 9, and 1. 1. And then finally, the next cup is clockwise from your current cup. So we're going to no longer have this be our current cup. The new current cup is 1 to the right of it. And it's just this, just this sequence repeated over and over and over. But anyway, that's one turn of the problem. Hopefully that helped you visualize that. And for part 1, the answer is the digits lined up after the 1 cup. So, in this case, if you had the 1 cup here, the answer would be 5, 4, 6, 7, 3, 2, 8, 9, and you ignore the 1. So that would be the answer. Of course, we do more than 1 turn, so that's not the answer, but that's how you figure out the answer. And I'm going to show you what I did for part 1. My part 1 solution is not the ideal solution, but it was how I was thinking about the problem at the time, and I eventually realized why this is slow, and I'll tell you that in a second. But anyways, to parse this, I used a collections deck. A deck is a circular buffer, which, this is a circle, so a circular buffer kind of makes sense to me. It's a double-ended queue, and so that means you can quickly pop and push from both ends. And it has a rotate, which helps you move stuff around to insert into the middle if you know the right index. And rotate is usually very quick. But we'll find that one of the operations I did was not very quick, and that's why this didn't scale to part 2. But yeah, I just parse the individual characters. Note that I use list on the input string here to get 1 character at a time, and then I convert those into integers and populate my deck here. I also find the maximum of the cups. I later learned that this is just the length, so there's no reason to use max here. You could just use len, because all of the numbers in here are unique, and they're 1 through 9. Then I have a loop over the number of turns, so in this case it was 100 turns, and then I just basically implement the algorithm, like grab the first cup, rotate once to move the cup off. So what rotate does is it moves this position to this position. Then I pop 3 items out, so I popped 8, 9, 1. Then I try and figure out the current cup label. This is a little bit of math. I was a little bit bummed that it wasn't 0 indexed, so I couldn't use like tricky mod tricks here. So I just had to check, is it 0? Okay, set it to the maximum. I probably could have done -1 mod +1 or something like that, but this is what I came up with on the fly and stuck with this in the end. Then this is actually the slow part of my solution. Index in a deck is ON. So, and for 100 turns and for a size of 10, this actually isn't that bad. But when we jump to part 2, which has 1 million items and 10 million turns, this index, blows that up substantially. So you would do, 10 million times 1 million operations just for this one line on average, right? Or in the worst case. Which is going to be way too slow, but it worked fine for part 1. So I find the index of it, I rotate the cups to figure out how to insert, I extend to add these taken cups into it, and then I rotate back to get to the next position. So this rotates back to where we were before. We add 3 for the inserted things, and then we add 1 for the rotate to the right bit. But that's how I implemented part 1. Mostly works, but again, like this index here is ON, and so it's going to be slow if you increase the number of, the number of iterations here. Oh, and then finally at the end, I, find the 1 index, rotate, pop off the 1, and then join all of the numbers together. So this is, just similar code for that. And note that I cheated a little bit and used the stringification and then integer parsing of the stringification. Like, I guess in other languages you would build up, in base 10 and shift the numbers over by multiplying by 10, but we can just use the int parsing function here. But anyway, that's what I did for part 1. When I tried to run this in part 2, this was extremely slow. I didn't even get to like 100,000 computed, and I had to do 10 million. So I was nowhere near the order of magnitude in order to complete this problem, and so I had to rethink how I was approaching it. And so for part 2, what I did, and this is actually a diagram, instead of using a circular buffer where I can't, index quickly and insert quickly, I switched to a linked list-like structure, but a circular linked list. So these kind of represent the nodes here. So you can see like this gets parsed as 3 pointing to 8, pointing to 9, pointing to 1, pointing to blah, blah, blah. And then eventually at the end, the 7 points back around to the beginning. So you get a circular structure here. I have a current pointer, which points to, well, again, it's not a pointer because I did it in Python. So these are just variable references. I have current that points to the current item, and this is just a variable. And then I have a nodes mapping. This makes it so I can really quickly look up individual nodes in this structure without having to, loop through all of them to find the right node. And so I have a dictionary that just maps 1 to this particular item here. And we never create or destroy these after the initial creation, so we're just adjusting this structure here. And so there's kind of 2 operations that you need after you've created this. There's, or 3 operations. There's remove 3 things, insert 3 things, and rotate 1. And so rotate 1 is the easiest. You just grab this next pointer and, adjust. Let's say we just adjusted current to now be here. So, that's moving this over. For rotate, for removing 3, what I did was, let's do red for that. So there's like 3 items here. You can very easily get, next pointer, next pointer, next pointer, next, and change the next pointer of this one to instead point here. And so that allows you to remove 3 items from your loop and, make the loop smaller. And then if you need to insert items, what you can do is, let's say we inserted after the 2 here. We would take 2. It's actually, it's going to look gross, but don't worry about it. Let's say we move this out over here. Yeah, this is gross. This is a bad diagram. Anyway. Let's say that we wanted to insert after the 2, which is what we did in there. We would look up 2 in our nodes, see that it's here, and adjust this next pointer to point to here, and then adjust this next pointer to point into here. And so that's how you can quickly insert stuff in there. So then all of these operations become O1, and we're no longer incurring that really, really slow lookup bit there. We're essentially, doing this almost instantaneously. Of course, Python's kind of slow, so instantaneously is maybe not the best way to think about it. But this is the code that I used to implement that. I made a node class, which represents my circular buffer here, and it has a member for itself and a next node. Note that I was able to do this with a singly linked list. My original implementation had a doubly linked list, but I realized none of my code used previous, and so it was simpler just to remove this. I also made a representation here. This is actually a little bit buggy. It doesn't work for this like pulled out fragment. It'll just loop forever. But what it does is it goes around the entire cycle until it hits itself, and then it just gives you kind of a representation of the numbers in a row. This made debugging a lot easier. I have append. This is what I use to initially build up the object. What it does is it builds another node, then it sets next to this, and then it says the current next is new node. So this is essentially an insertion. And then it returns it back, so you can kind of chain this append over and over and over. And then I had pop3 and push3. I probably should have just done pop in a loop, but this this seemed to be, the cheesiest, easiest way to do this. And so I kind of had this gross next node, next node, next node, next node to remove the 3 items. And then next node, next node, next node to insert the 3 items. And so those are the operations that I had on my actual node class. And then my compute function. Oh, right, we have to do some other math here. I forgot to talk about that. We're supposed to fill all the cups after up to 1 million with incrementing numbers. So this is just like, filling in a range after that. That's what this bit does here. And then we run 10 million turns. So I set n to 1 million. That's the numbers that we fill in here. And then we run 10 million turns. Oddly enough, I spent like 20 minutes on this +1 here, which is just my bad. Yeah, and this is how I build up the initial structure. So we grab the first number, build a node out of it, and that becomes our appender. And we just do appender.append each time. And note that I'm keeping track of all of the nodes so that I can reference them in O1 later in this mapping here. And then this is just appending all the numbers up to 1 million. And then this is our algorithm here. So what we do is we take 3, so we pop 3. I used a set here because we need to loop over and figure out when we're not a number that is in this taken set. So I just build a set out of the 3 ends there. And this is essentially the same code as I did for part 1, where I just, if it's 0, wrap around to the end, and then continually subtract 1. This could have been minus equals 1. I don't know why I didn't do that. And then finally, once you find your target node, we can access it directly, do push 3 to put those taken back after that one, and then do this to rotate. So I felt like, this was pretty straightforward after that, but thinking about this circular structure was kind of tricky. Interestingly enough, in an interview in 2012 for Amazon, I actually implemented almost the same structure for a caching implementation. I also used this in a page tracker, memory page tracker, in my operating systems class in college. But it didn't. This didn't click until like 30 minutes into working on this problem. But anyway, and then at the end, we access the next node after node 1, and the next node after node 1 to get our answer. Even with all of this, this solution is still pretty slow in CPython. I think it took like, I don't know, 25 seconds to run, and it'll probably be even slower because I'm recording. But it does complete, whereas the DEX solution would have taken several years to complete just because I, went from O1 operations to ON operations. And I don't know about you, but I don't have a year of CPU time to run this problem, and so reworking this to a linked list made it so it was solvable. But anyway, that's my solution. That's how I approached it, as well as the problems that I had with part 1. And yeah, if you run this with PyPy, it's like 4 seconds. And if you compile this with MyPyC, which is it basically builds C extensions for MyPy typed code. This gets down to like 6 seconds, which is pretty impressive for CPython code, for essentially just taking pure Python code and compiling it into C for free. It's pretty neat. But anyway, that's day 23. Hopefully this was useful, and I will see you for day 24.